Hey guys, so today we're going to be doing lab a little bit differently today due to the weather. And I hope this video helps, but we're going over one way between subjects ANOVAs. Um, and we'll be doing question two, how to do it by, first we'll be going over how to do it by hand, and then we'll go over how to do the same exact thing in R, but with a few more steps. You guys can obviously read this example, but essentially this developmental psychologist is testing problem-solving abilities between three groups of children. So he has a group of, or they have a group of, 5-year-olds, a group of 6-year-olds, and a group of 7-year-olds. And within each sample, there are 3 children, so we have a total of 9 children, right? And we're trying to figure out whether there's a significant difference between 5-year-olds, 6-year-olds, and 7-year-olds. With an alpha of 0.05. Much like the other tests that we've been running this semester, we'll show 5 steps, although these steps will look a little bit different because this is a completely different test. And we've been training for weeks, guys, but I think we can do it. Report the results in APA style. And I'll obviously show you how to go over that as well. So first, we'll be stating our hypotheses. The null hypothesis is that there's no difference between the 3 groups, and the alternative hypothesis is saying that there is a difference between the groups. At least one of those groups is different from the other groups. And then we set our decision criteria. So we have our alpha, which is 0.05, our degrees of freedom between, which is k minus 1. So k being the number of groups, minus 1, which is 2. And then the degrees of freedom within is n minus 1 for each sample. So there's 3 children within each sample. So 3 minus 1 plus 3 minus 1 plus 3 minus 1, which gives us 6. And now we have to figure out our F statistic. We have the degrees of freedom between, so that's 2, and then degrees of freedom within, which is 6, and that should give us 5.14 for our critical value. Now we're in a good position to start solving this. Now, step 3 is probably going to be the longest step here, but it's essentially because we're working our way from one end of the equation to another. We need to find between group variance and divide that by within group variance. And in order to do those things, we need to find the sum of squares. We have our degrees of freedom between, and we have our degrees of freedom within. But there are some values that you guys can see that we don't have. So this right here is essentially telling you what the F statistic consists of. So the variance between these 3 age groups, and then the variance within each one of these groups. And this is what they equate to. And this will all make a lot more sense in a little bit. So first we need to calculate the sum of squares within. And if you go to the Excel spreadsheet that you've been given, I believe it's on the lab as well, these values should be there as well, and you'll need that to run the ANOVA, but we'll get to that in a little bit. So you can see each one of these groups has 3 sets of scores underneath, 1 for each participant. And you'll see the equation for sum of squares, within is equal to the sum of y, for whatever group that is, minus the sum of, so the same value here, the sum of y for whatever group that is, squared, divided by n, the number of participants within that sample. So here it would be 3, subscript 1. So this is just alluding to this group right here. But it could be a 2, it could be a 3. So we can sum all of these now to get this value here. So the sum of all y, the sum of all of the scores for 5-year-olds is 15. And we can also, I'm getting a little bit ahead of myself with these terrible transitions, but calculate the mean as well. So you guys know how to calculate the mean. We've been doing that all semester. And you would do that for each one of these samples here. Another thing that we can do, because we're literally summing the squares within each group, is literally squaring these data points. So 5 squared is 25, 4 is 16, 6 becomes 36, and we can do these for every single group. And then we can add them up, and you'll see why in a little bit. And by the way, I do want to mention that the sum of all of the 5-year-olds' scores squared is not the same as this value over here. Um, and again, getting ahead of myself a little bit, but we had actually all of the necessary information to calculate the sum of square uh, for the first group. So it would be 15 minus, and then in the numerator here, we would have 15 squared, and then we would divide that by 3 because the first group has 3 participants in it. And you would essentially do this for every single group. So there's a sum of squares within for every group. Right? And then we have to add those up, and then we get a total sum of squares that we'll use later. But first, yeah, so this is just saying so we took the sum of squares within from each group, so 2, 8, and 2, respectively, and that's 12. So just keep that number and set it aside, basically. And now we have to calculate sum of squares between. But we also, in order to do this, we need the grand mean. So that's like the mean of the means, basically. And to calculate that, you would take the means that we've already calculated from each group. So 5 plus 4 plus 1, and then you would divide that by the number of groups. So this should be k here. So the reason why we need the grand mean is because we need to subtract the mean for each group from the grand mean. So like each group has its own mean, but then there's a mean of means that kind of like the mean of means for between the groups, if that makes sense. So means within and then means between. This is the mean within, and then this is the mean between. And then we have to square it here. This should not be here. Excuse this equal sign, guys. But essentially what this is going to look like is, so n for the first group here for 5-year-olds, n is 3. We have an average for this group of 5. And then we subtract that from the grand mean, which you guys didn't know was 3.33 because that's not on the screen right now. And then we make sure to square that. And we do that for each group. So you'll see 4, and then you'll see 1, and they're subtracted from the same grand mean. And be careful, be mindful of your order of operations here. But you should get 26 total. Now we can create the ANOVA source table. We have all of these, most of these values here. We had the sum of squares between, we had the sum of squares within already calculated. We already know what the degrees of freedom between are and what the degrees of freedom within are. And then make sure to get these totals down here for sum of squares and for degrees of freedom, literally by just adding the between value and the within values. Excuse me. But now we need to get mean squares, right? Mean squares between and mean squares within. This is very simple. So we just take sum of squares between divided by degrees of freedom between. 26 divided by 2 is 13. And then same thing for within. So 12 divided by 6 is 2. And then we can populate that source table. And our F statistic is going to be the mean squares between divided by the mean squares within. And that'll give us 6.5. And now we have to make a decision, much like we have for all of our other tests. So we compare our observed statistic to our critical statistic, and our F statistic, or observed F statistic is larger, so that's 6.5, that's what we just calculated, is larger than the critical value that we found at the beginning before we started going through this example of 5.4. So we would reject the null hypothesis. And obviously, we need to put that in APA format. So one-way between subject ANOVA tested whether there was a main effect of children's age, and then we give the three groups, or all of the groups that were tested, on their problem-solving abilities. Results showed that children's age had a significant main effect on their problem-solving abilities. And then we have our F statistic here is italicized. We have our degrees of freedom between and our degrees of freedom within in parentheses. We have our observed statistic here, 6.5, and then P is less than 0.05. That's the alpha we were using. So similar to what I've been telling you guys in lab, a lot of this stuff, it's very formulaic. So like here we did the type of analysis that we ran, right? And the levels of the independent variable, you need to specify that for the reader. Although they could probably figure it out with your degrees of freedom, it's really nice to let people know what you're talking about. And then whether there was a main effect or not, so results showed that children's age had a significant main effect on their problem-solving abilities, and then the actual result. And it doesn't necessarily have to be, I mean, if P is less than 0.01 or P is less than 0.001, that's much better than 0.05. So that's kind of what I tried to put right here. So, okay, we know it's significant, but where are these differences coming from, and how strong is this difference, if there is one? Well, we know there is one because of the significant main effect that we saw. So we get into effect sizes and pairwise comparisons. Excuse this right parens here, but who cares basically about effect sizes? Well, we need to figure out whether these group differences, like a difference, we know that the result is significant, so we know that there's a difference. But that only tells us one thing that we need to know. We need to know whether these group differences are large or small, and we also know where, we need to know where these differences are coming from. So within the level of the independent variable that we're using, 5-year-olds, 6-year-olds, and 7-year-olds, is it between like 5-year-olds and 6-year-olds? Is it between 5-year-olds and 7-year-olds? Is it between 6-year-olds and 7-year-olds? We don't know. First, we can give the effect size, which you'll see later how that gets incorporated into APA format. But eta squared is the effect size, and that'll tell us the amount of variance in the dependent variable that can be attributed to the independent variable that we use. So we have all of these values here with 26 and 38, right? That was our sum of squares between, and then we had our sum of squares total. So our eta squared is 0.68. So that means that 68% of the variance in children's problem-solving ability was accounted for by their age. So here's the DV, which is accounted by the IV, 68%. Maybe it would be better if I showed you guys what's going on with R before we continue this. So we're essentially going to be running results, running the same exact test. I mean, we already know what the result is going to be, but it'll make sense why I'm giving you guys this screen as opposed to just talking at you. It'll make more sense why in a second here. So first, you have your data. You guys know how to import Excel spreadsheets into R, and then make sure to specify it, specify the name. So I'm going to run it. just to make sure, and then this little guy should pop up. So I have my own Excel spreadsheet that I've made. I think your columns will look a little bit different, like ind and then something else for your dependent variable, or excuse me, independent variable. It's essentially the same exact um, placement in terms of like where you would put your independent variable and where you would put your dependent variable. So to conduct the one-way ANOVA, this is what I was talking about. So we have to set results. You can literally call this whatever you want. You can say like lab 6 results, whatever. Just be careful, be mindful of spaces. AOV is the command for ANOVA. And then score is our dependent variable. That's what I had as my dependent variable. And age is the independent variable. And then we're asking R to take this data from lab 6, which we've already imported into R, and then give us a summary of these results. So let's run it. Wow, crazy, right? I'm not sure. Hopefully you guys can see this, but the sums of squares between residuals will refer to within subjects. So we have 2, 2, 6, 6. Sum of squares 26 and 12. It's inverted in the R output, but it's the same exact information. It gives us this really nice p-value here that we can use to actually, um, we can just leave it actually, it's less than 0.05. And that's denoted by the asterisk as well, if you don't feel like doing quick math in your head. And as I was saying before, we need to know how big of a difference this is and how, like where this difference is coming from, right? And remember when I was telling you guys that the effect size can tell us the amount of variance in the dependent variable that can be attributed to the independent variable. Although you can calculate it by hand, it's nice to do it in R as well. And in order to do that, you'll need to download SJStats. You can either, I know some people have been doing the install command. Usually what I do is I'll just go to packages, install, and like anything that you want, SJStats, see that? It popped right up and then it hit it and then I can install it, but I already have it installed, so it's not going to do anything. And then you'll run eta squared. So our eta squared is 0.68. And then you don't really have to pay attention to this confidence interval for now, but just know that 0 was not included in this confidence interval, meaning that this definitely was a significant finding. So this is where we got this 0.68 from. We can get it from here, and now we know how to do it via hand calculation. So sum of squares between divided by sum of squares total. And now we have to run pairwise comparisons. That'll tell us where within the levels of the IV these differences are coming from. So again, we're essentially doing t-tests here. We're doing 3 t-tests to compare 3 groups. So we're doing 5-year-olds versus 6-year-olds, 5-year-olds versus 7-year-olds, and 6-year-olds versus 7-year-olds. And to do that, we can run pairwise dot t dot test. Make sure the name of your spreadsheet is correct. Make sure your dependent variable is correct, commensurate with whatever you've labeled it as. So again, yours is probably going to say IND, but I entered mine in manually, so mine says score for the dependent variable. And then for the independent variable, I have age. And we're going to be using a Bonferroni correction. And I'll tell you what a Bonferroni correction is in just a second. But let's run it. And so we can see right here, these are p-values. And what Bonferroni does is essentially adjust for corrections. It's a very conservative test that's used to detect uh, differences between groups when we're doing pairwise comparisons, also known as post hoc comparisons. And the reason why it's conservative is because it's less sensitive in terms of detecting differences among groups, depending on the variability across those groups or observations, whatever that you're testing. Um, and it has less statistical power in that sense. Like, I'm not sure if you guys will go over Tukey, but that's also another type of post hoc test that you can run. It all depends on the variance of the um, observations or groups that you're looking at. But for the purposes of this, we're going to be using Bonferroni to run these pairwise comparisons. So we can see these are p-values right here, the 1.0, 0.04, and 0.12. We can see that the difference between 6-year-olds and 7-year-olds is p equals 0.12. Okay, that's not significant. We can see the difference between 5-year-olds and the 6-year-old groups, excuse me, are 1, which is not significant. But between 5-year-olds and 7-year-olds, we see a p-value of less than 0.05. So that's exactly what we would say um, in our results. Excuse the terrible memes, you guys, but so before this is what we had, right? We didn't even have the partial eta squared here. But now we have all of that and more, and it tells the reader so much more. So here, as I said in the previous slide, like you'd add this on and say, which accounts for something along the lines of which accounts for roughly 68% of the observed variance. And then we also just conducted pairwise comparisons using the Bonferroni correction, which suggests that problem-solving abilities were significantly higher for 5-year-olds compared to 7-year-olds. And look at their means right here. Like, this is why we always include means and standard deviations. They have the same standard deviation, but the means are higher. But how would you know if you didn't include the like, the standard deviation tells you a lot, is pretty much what I'm trying to say. Um, and remember, we have to, like, this helps paint a picture for the reader. So that's why we always include the mean and standard deviation. For the purposes of this assignment, I only included where the significant difference was, and that was between 5-year-olds and 7-year-olds. But it's really good to let the reader know that, um, like about the other results and what happened there. So as you can see here, it doesn't give you the means and standard deviations. It just tells you what the p-values are. So you'll have to do that manually. The mean you already have from the hand calculations, but then you can get the standard deviation through R if you don't want to calculate that by hand. What really helps paint these results, paint a picture for these results, is visualizing them. So ggpubr is another package, another package that I highly recommend you guys install through packages install, and then ggpubr if you don't have it already. But I have it installed. So this is the command that you'll enter, ggline, and then this is the name of the spreadsheet. Our x-axis or independent variable is going to be age, and then our y-axis or the score, our y-axis or the dependent variable is going to be the score. And we need to tell it to calculate them or add the means as well. So you'll see in this screen right here, Yeah, looks like there was a big difference. 5-year-olds took the cake, man. Highest score. Um, and our post hoc comparisons told us that there was the biggest difference between 5-year-olds, the 5-year-old group and the 7-year-old group of 0.04. So if you can look at this graph here, look at where 5-year-olds scored, and then look at where 7-year-olds scored. They scored a 1 for some reason. Um, so that's why we do these pairwise comparisons, is because we know the result is significant, but we don't know where they're coming from. And furthermore, we need to tell the reader how powerful these results are. Like what, how is our IV accounting for our DV basically? And that's why we throw eta squared as well. So I believe that concludes it. I will see you guys in lab in just a little bit. Feel free to stop by if you have any questions, but because I'll be available from the normal time, or just shoot me an email or whatever afterwards. See you in a bit, guys. Thank you.